Lithium-ion batteries are the leading technology in powering most of our everyday electronic devices, like phones, laptops, and even the modern-day electric vehicle. Lithium-ion batteries consist of a number of power-generating regions called cells. The electricity is provided to the cells via two metal contacts. In this case, the metal contacts are aluminium and copper. Beyond this, these cells are fundamentally made up of three components: a positively charged electrode, a negatively charged electrode, and an electrolyte solution. The positive electrode is typically made of a lithium metal oxide, but in some more recent batteries is instead made from lithium iron phosphate. The negative electrode is made usually from carbon, graphite, while the electrolyte solution varies from one battery to another, but essentially acts in the same way.
All lithium-ion batteries work in essentially the same way. When charging, the lithium cobalt oxide at the positive electrode loses some of its lithium ions as it undergoes a forced chemical reaction and begins to store chemical energy. These ions travel through the electrolyte from the positive electrode to the negative before recombining with their lost electrons on the graphite at the negative electrode. When discharging, the reverse reaction occurs and these deposited ions flow in the reverse direction from negative to positive, recombining with the lithium cobalt oxide at the positive electrode. The flow of electrons is simultaneous to the flow of ions in both cases. However, due to the electrolyte acting as an electron barrier, they are forced to run through an external circuit where they are able to do useful work.
Lithium-ion batteries are superior to dry lead-acid batteries in the majority of aspects other than cost. They achieve close to 100% efficiency while charging and discharging, while lead-acid batteries can have up to 15 amps loss while charging. As well as this, they may be discharged 100% of their capacity as opposed to 80%, and have a lifespan of over 5,000 charge cycles rather than 400 to 500. As they are a third of the weight of lead-acid batteries, they are ideal for modern electric cars and handheld devices. They are a much more environmentally friendly option, with their higher upfront costs being made up for their substantially higher efficiency and longer lifetimes.
Various circuit models are widely used to represent and simulate the operation of lithium-ion batteries. These circuit models all stem from the most basic circuit representation for a lithium battery, the RINT model. This model uses a capacitor acting as an ideal voltage source to depict the battery's ability to store chemical energy, along with a resistor in series which accounts for inefficiencies. Improvements to this model include an additional capacitor in parallel with the first, along with additional resistors to model the surface effects of the battery. Further improvements constitutes a Thevenin equivalent circuit which more accurately demonstrates the transient effects when charging or discharging the lithium-ion battery. Final improvements are made on the circuit model to account for polarization factors of the battery, as shown in the circuit diagram. This circuit representation is known as the dual polarization (DP) model and is the most accurate representation of those previously shown.